So finally, for this session, we have Sam Kitajima-Kimbrel. He works at Twilio and has been working for the past 2 years on maintaining and scaling the Twilio REST API. So he's very much a Python enthusiast for many years. And please welcome him to his talk from the Flying Circus to Holy Grail, migrating the Twilio API from PHP to Python. So off you go.
All right, can everybody hear? Great. Thanks, Ember. So yeah, I have a question for the room. Put your hand up if you've ever wanted to take some janky old piece of code that has 200,000 lines and does everything your entire business operates, and just tear it up and rewrite it from scratch. Great. For the video, the room is full of hands. Keep your hand up if you've pulled this off. 1, 2, 3, 5, 6. Okay, so clearly we've all seen this go wrong, right? So our old code sucks. Let's rip it out and redo it. We fast forward 12 months, and yeah, project's fallen off the rails, or we didn't get to where we wanted to get, or we deployed to prod and it fell over 12 months later, right? So since I'm standing here, there's obviously a better way. So hi, I'm Sam. That's my Twitter handle. I have opinions there. I worked for Twilio for 3 years. 2 of those, like Ember said, were on the API team, where we did, in fact, migrate from our 7-year-old flying circus of PHP code to the holy grail of Python and federated services. Today, I'm going to talk about techniques for replacing old code using this project as a case study. If you're not familiar with Twilio, real quick, we provide communications as a service. So as a developer, you can use our platform to build communications, so phone calls, text messages, MMS, WebRTC, many other things these days, into your app wherever you need to. To put some context on here, the REST API is very critical to our platform. It exposes all of our entire feature set, and at peak, we now process 5,000 RPS, and we maintain over 4 nines of uptime. So with that in mind, I'll start with a really brief overview of the Twilio architecture. So ancient history, in 2008, we had pretty much one product. It was Twilio Voice. You can make phone calls using our API and direct them in real time. It's still pretty cool. And we also had exactly 2 code bases. We had the Twilio Voice stack, which was written in Java and handled everything that actually involved picking up a line to a carrier and making a phone call happen, moving media back and forth. And we had PHP, which did everything else. So we had the website, the API, the billing backend, our internal admin tools, and pretty much everything in PHP. So it basically contained a core set of domain objects and models and business logic for running Twilio. As time went on, this code base grew and grew and grew, and we added more features to it, right? So by the time we launched SMS, oh, I totally missed something in here, I'm sorry. Go back to this. The database in the middle is how the 2 systems communicated. So you would make a request to the API to enqueue a call. PHP would authenticate you, validate your request, and then drop a row into the calls table that said, we'd like to make a call now. Java, on the other side of the world, would be pulling that database and pick up the init state calls, pick up a phone line and make a call happen, and then write state back in that you could then query through the API. There we go. Got the missing piece there. So yeah, by the time we launched SMS, we knew how to queue better. MySQL is not a really great queuing system. But we still relied on PHP and the database for just about everything else. So again, as we added features, there might be a little smarter logic for the real-time constraints, but retrieving your records of everything you've done still just went straight through some PHP code and hit a database. 5 years later, we added a lot more things, and our API just kept growing like this until about 2013, when we realized we had some problems. Problems like difficult deploys. Deploying all this PHP code was difficult. It ran 12 or 13 different roles, but it's a single repo. All these roles processed multiple functions, but the core logic was shared, right? So we had all these business objects that were shared between the website, the API, and so on. Changing something to make it work better on the web or implementing a new feature might very well break the API, or vice versa. So we'd always end up pulling together massive release candidate branches and locking 10 developers in a room for 2 hours to verify everything against stage. And by I say verify everything, I mean everything we knew about. We also had a not great in testing situation. This took hours. The system was difficult to understand in kind of 2 senses of the word here. First, the code had grown so fast that it was not very well organized. Figuring out what lived where and why usually took a senior dev and half an afternoon. And it wasn't well instrumented at all. And so in production, we never took the time to go through and add fine-grained metrics to the system. And so things would slow down in production. We'd have no clue why. And finally, it was operationally brittle. In the REST API, this surfaced with one major flaw. We were running a single fleet to handle the API traffic for all of the API resources. And those resources varied widely in their access patterns and how they performed. So making a new call or sending an SMS message returns in 100 millis. But if you go and ask us for 1,000 calls from 2 years ago with a to and from filter, might take a couple of seconds to dig that out of MySQL. Add in synchronous I/O, thanks to PHP as well, lack of anything else. And we ran into trouble really quickly. Look like this. Any slowdown in a single resource, even if everything else in the system was healthy, would quickly exhaust the synchronous worker pools on our PHP FPM servers and take down the entire API. So we couldn't serve any traffic, even to unrelated resources. As an API platform, we are deeply ashamed of this. It was the worst possible failure mode for us. We couldn't take traffic from customers for things that should have worked because something else was slow. So to recap, we've got 500,000 lines of PHP handling this critical part of our business. It was failing to scale with both of our customers' traffic growth and the growth of our developer team. And from accumulated wisdom, we knew that if we set out to rewrite this thing in one go, we would almost certainly fail. So instead, we decided we were going to take it apart and replace it bit by bit. So to more context on this, thankfully the API team wasn't in a vacuum over those couple years. The rest of engineering had figured out that service-oriented architectures were a good idea. So for those not familiar, SOA is when you have a fleet of small single-purpose services working together in concert to solve your problem instead of a single giant monolith of one code base. This grew out of work done at Amazon. If you haven't read the Steve Yegi post on Jeff Bezos' mandate about services, you should. It basically outlines how you should build large distributed systems like this. And we built a few of these, and actually had managed to even hook up the PHP API to a couple of them because we didn't want to go back and build it the other way. It looks like this, right? So like I said, inspired by Amazon, the core rule here is that no system is allowed to use code or data from another service. So you cannot link anybody else's libraries. You cannot access their database directly. Everything has to go over the official interface of that service over the network. So we picked REST as our internal API standard. And we started thinking, because of that, well, we've got all these internal REST services, and our public API already speaks REST to our customers. Can't we just map one to the other and call it a day? And so we did. We built a simple, powerful app for transforming and routing REST requests. We identified the internal systems that had grown to feature parity with existing API endpoints, and we cut them over. We call it Starship. It's built in Python. Yes, it's the API Federation, the next generation. That's the joke. It's built in Python and Flask. We actually open sourced the Flask RESTful framework, which powers the REST endpoints inside of this Flask app. And we use requests to do HTTP to our internal services. As of the end of 2014, it handles 100% of Twilio's API traffic. And this architecture and this system solve everything that we disliked about the PHP architecture and some problems we didn't even know we had. So to recap, the architecture now looks like this. We have this wide array of internal services that implement all of the Twilio platform functionality and expose internal REST APIs for that functionality. Starship acts as the public front door to all these systems and unifies their APIs into the public interface. And critically, which is what really the huge win with this project, is that Starship provides all of the common pieces of the public API. So authentication, validation, rate limiting, feature rollout, et cetera. It lets our product teams not have to worry about doing all those common things. So if you're an SMS team, you don't have to build authentication for your new service when you stand it up because Starship provides it for you. We call this the proxied resource pattern. And in brief, given an external API and an internal service that implements something that does the semantic work of that API endpoint, but might be formatted or structured differently because we have a lot of data internal to the platform that customers don't need to care about, we define a mapping from one to the other. So for example, Here's what the internal and external representations of phone numbers on the Twilio platform look like. Don't worry about reading this. Just kind of look at the shape of this JSON and say, like, they're similar but not the same. And so Starship maps from one to the other. And the core of Starship is a configurable engine that can apply all of the transformation steps to a request, send it off to the internal service, and then take the response, transform it back to what the customer expects, and return that. And these days, we just write config files to define both sides of the API. So we have a config file defining the public interface, the private interface, and any transformations necessary to get from one to the other. So the framework takes care of the rest. It's extremely quick to add or modify resource definitions. You usually don't have to actually write any code. You just map something out in a JSON file, rebuild the service, and redeploy, and out it goes. So there was a huge amount of risk involved in migrating all of our API traffic off of a system that we knew worked and had worked for 5 years, even if it had some operational issues. But there's also a lot for us to gain. So first of all, we fixed the deployment problem. So these days, adding API endpoints or making changes to existing ones just means modifying the configuration for Starship. And the teams responsible for the internal systems that build the logic can actually deploy whenever they want without worrying about breaking other pieces of the platform. We use automated testing heavily on both sides and across the service boundary to ensure that we don't break things as we roll forward. We gained a lot of flexibility. We used to be just in PHP, and we would have to, if we wanted to change something to be about how a request was handled, we have to go write a bunch of code. And Python now means we can route and handle requests and do whatever we want with them based on pretty much any aspect of the request. We've added features to Starship that let us do randomly selected requests for A/B testing or percentage-based rollouts, account flags. We can even shadow internal reimplementations of services or release candidate versions without disrupting the customer-facing response. And we fixed all of our operational issues. So Starship is much more fault tolerant. We use async IO, not actually async IO, it's G-event because we're still in Python 2. But using async IO means we can handle orders of magnitude more in-flight requests. So we no longer fall over just because one thing slowed down. Starship also gives us a single place to instrument all of our traffic, which gives us a huge amount of insight into how our infrastructure is performing. So for example, this is a chart of latency to API resources grouped by the internal system that handles the resource. And this lets us watch how things are performing day over day, week over week. We can anticipate growth and fix problems before they become outages. And similarly, here's the API request latency to a single endpoint with timers over every phase of the operation inside of Starship, right? So that in the initial processing phase, authentication, the actual dispatch and waiting for the internal service to return, and so on. This looks scary. This is actually just seasonal write traffic causing our database to get a little bogged down. We're still in the tens of milliseconds on this chart. But importantly, we could look and say, like, if, for example, this were the offline, we could say, oh, did we deploy the authentication service? Why did that slow down? Both of these things we had no idea before, so it's extremely powerful. So Starship is awesome. But how do we do this? How do we move all this logic to these new services and safely move the API traffic over? That's what I'm going to go through for the rest of today. Starship wasn't a new idea at Twilio. It came about in 2012 or so, but it took us a while to decide we wanted to go all in and deprecate the old systems. And I'm going to go through how we planned that movement, that migration, the intermediate architectures we chose, and how we tested and deployed this. So first up, planning. If you want to go and rip out your legacy code and replace it piece by piece like this, you should have a plan. I recommend it. So really, the core piece here is you should identify the granularity at which it makes sense to break apart your legacy monoliths. If you go too low, you're going to spend all your time moving tiny pieces one at a time. And if you go too high, you're not actually going to get any benefit because you're just going to have like 2 or 3 monoliths instead of 1. You should make a list of what you're going to replace and order it. The ordering should look something like this. You should start small. So start with a couple things that aren't so mission critical or lower volume. But at the same time, there's also a competing drive here, which is that you want to start realizing the benefits from this project. The benefits are going to come from moving the big stuff that powers most of your business or most of your app. Because that's where you're going to reap the most benefit by unblocking all the other developers who want to add features or make improvements to those systems who are stuck waiting for stuff to happen in your old legacy code. So that's planning. Next up, architecturally, you should think through what you're doing. Please don't just pick up a machete and start hacking things off. You should pick off reasonably sized chunks and deploy them one at a time instead of one big bang cutover, which is the point of this entire talk. And this sounds hard, right? But fortunately, Wheeler's fundamental theorem of software engineering applies, which is that we can solve any problem by introducing a layer of indirection, except for too many layers of indirection. So we apply this, right? Add some sort of shim to your system. Think of it as a way to dispatch between your old code, thank you, and your new reimplementation based on a function call or request, some attribute of the work you're trying to do. And like I said earlier, the most critical piece here is to find the right level to add this at. If you go too low, you're going to spend all your time configuring your dispatch module. And if you go too high, you will not be able to work in chunks that are small enough to deploy safely and quickly. For us, to give an example, the right place to do this was in our HTTP server. So we ran both Starship and the old PHP code behind Nginx on a single host, using it to request, or a single fleet of hosts, using it to route requests to one or the other based on the method and path of the request. So for the long time, post to the calls endpoint to start a new call went to the PHP implementation because it was kind of the oldest thing. We knew it worked. We didn't want to touch it until we'd proven ourselves. And then we started moving, messages went first, right? Messages and phone numbers and so on moved into Starship. Most importantly, keep this dispatch layer simple because depending on how big your code is and how large of an undertaking you're going into here, you might be running with this in place for a long time. So making sure it's something you can debug, make sure it's something that performs well, and so on. And once you have a way to control which system is used where, you should think about how to test this implementation. Confession here, if your legacy systems are anything like Twilio's, this is a blessing and a curse. You have a great opportunity to improve your test coverage, but you might be starting from, let's go with not much. Unfortunately, there are a few tacks to take here. I'm going to talk through a little bit of testing theory and architecture. So really core to this is that you should test in multiple layers. This is actually one of the more useful things to come out of the Agile movement. It's called the test pyramid. And it's really about boundaries. So if you have some piece of functionality in your code base that you need to test, you should identify the right level to test that at, the right set of boundaries to cross or not cross in order to assert that the code does what it should do. As you go up the pyramid, your tests are going to be slower to write because you have to deal with more of the world as you have crossing more boundaries, either mocking them or using live services. And they're going to be slower to run because you're exercising more code. So choosing the right level of the test pyramid to write your test cases at lets you focus your effort appropriately and test at the right place. So to walk through how this works for Starship, it's something like this. Our unit tests are the internal logic of Starship, right? So given a username and password to the API, do we authenticate correctly? Do we transform JSON correctly? Do we correctly strip out internal fields from a response? We call the functions in isolation, right? So this is at the level of individual functions inside the code. And you might have to mock out a few things here if you have side effects. But to talk to that aspect of speed, there are about 1,200 tests in this set, and they take 3 seconds to run. So this is very much the thing you run after every commit as you're working in a branch, right? Make a change, commit it, run the tests. Are you green? Keep going. If not, fix it. The next level is integration tests. So this is external to the Starship proxy engine, but with a faked out client and internal service, right? So we put a mock object on requests to fake out what we're going to do internally and fake out the client. And so the question here is, assuming the correct dependencies, does the Starship engine with the configuration for its endpoint do the correct thing? So there's several hundred tests in here, at least one to cover each API endpoint and method, and they take about 30 seconds to run. And then next up we have cluster tests. You might call these functional tests, end-to-end tests, or acceptance tests. They run against a complete Twilio cluster in our staging environment, and they assert that Starship works correctly in concert with all the other services in the system to implement the API. Critically, you have to run these when either side of the interface changes, because if we change Starship and suddenly break something, we'll want to catch it, and if the SMS team changes something in their service, we want to catch that too. There are a couple dozen tests in this suite, and they take about 5 minutes to run because they're hitting live services and actually doing work. And finally, when we're making large changes or adding new endpoints to the API, we'll do manual acceptance tests. Usually we'll sit down with a PM or a lead engineer from the other team who's exposing something and assert that everything works correctly. And these often form the basis for new cluster and integration tests. We save those responses and can them and put them into the automated suites. So that's kind of a little bit of testing theory, or the test pyramid, good best practices there. And next up, you should reduce overhead in your test cases. Make it easy to write test cases. Otherwise, developers won't. A lot of the time, you end up writing test cases that look really similar. So for us, right, take the example of authentication, right? We need to test that with a correct username and password, we authenticate. We need to test that with an incorrect password, we fail to authenticate. We need to test it with an incorrect username, we fail to authenticate, and so on. So automate as much of that as you can, right? So usually this looks like you'll have some function you're calling or a service endpoint you're hitting, and you'll do a bunch of setup, and then you'll put some stuff into it, and then assert a bunch of things. Automate as much of that as you can because you want to reduce the boilerplate and copy paste code because changes will hurt less. Fortunately, testing frameworks come to our rescue here. This is a toy example for using nose tests, if that's your runner. What you're using here is you define your actual test logic as a generator function. As the function on the bottom, and then you set up your sequence of all your test cases to run through it, and then just yield test cases from that. And the nose runner is actually smart enough to pick all those up and treat them as individual test cases. This is a toy example, but you can see what's going on here. And then similarly, this is what it looks like for PyTest. It's a decorator instead of a generator, but same idea. Right? We write a function that does some test logic, and we call it with a whole bunch of different arguments. These are toy cases, obviously. In the real world, your test cases will have 10, 20, 50 lines of code. And the benefit is much more apparent because you have one definition that you can change once instead of 100 copy-pasted versions that you have to go change 100 times. And finally, you can write throwaway tests. Sometimes tests shouldn't live forever. The example I'm going to give here is response diffing. So we are moving from one system to a system that needed to work exactly the same way. And so we had a reference implementation to check against. And so what we did was run the requests against a known good, right? So run a bunch of requests against the PHP implementation of the API, save the results, right? And then go to Starship and the new services and run those same requests, and then just do a byte for byte diff of the output. These are really fast to write, they're really easy to run, and they're extremely brittle. So if they pass, you're golden. And if they fail, then you have to go stare at some diff and figure out what changed. And most importantly, if you don't save them, right? Because if you use these as a crutch for your testing effort, then every time you change something, if you change the formatting of your responses or any other thing that is semantically the same but maybe syntactically different, you have to go review byte for byte diff to figure out why your tests failed. Don't bother. Use these to verify that your reimplementation functions correctly, and then throw them away and replace them with test cases that actually hit what you need to test. So that was testing. So like I said, you should write multiple sets of tests to test things at the right level. You should identify and accelerate the common cases. And machine generate tests for your systems when it's useful, but don't rely on those long term. So let's talk about deployments. I think everybody can agree that deploying code should be easy. It should be small to minimize risk. Your deployments should be fast to minimize the overhead. And they should be simple. So every time a human has to do something to deploy your code is a chance for you to screw it up. So you want to minimize the complexity of your deployments and then get rid of the chances for error. There's a lot of writing on this. I don't have time to dig in. Basically, it comes down to automate everything. Just get the humans out of the loop, automate wherever you can. I'm going to talk about a couple specific techniques for doing things like replacing legacy systems that are actually more useful. So here's a couple extra tactics once you have the mechanics of whatever your deployment pipeline is. Shadow deployments. This might also be familiar to you as dark launching. All you do is you deploy both versions of a system in production, and then put something in front of them that copies the requests and runs them against both your original system and your new system, and then diffs the responses. So this is effectively a high-scale automated version of response diffing tests using your customer traffic to produce the breadth and load against your system without affecting the live responses, right? So the golden rule here is always return the response from the known good. Don't return from the new. There's one big problem with it, though, which is that you can't do this for anything that changes state, right? At least not without doing a lot of plumbing to get your idempotency flags throughout the system. So for that, we turn to canariang. This comes from the phrase a canary in a coal mine, and the idea is you just launch one host with your release candidate rather than a full fleet, put it in the load balancer alongside the current implementation, let it serve whatever percentage of traffic it gets, and watch it for errors. So this is safer than a full deploy because if you do screw up horrifically, you're only screwing 5% of your customers. And it's faster to roll back is the big piece, right? If you have to flip 30 hosts in your load balancer for a full deploy, that's going to take 5 minutes. If you have one, it's gone in 10 seconds. And then finally, we have our low friction deploy system, and we have our extra techniques for ensuring safety, and we want to conquer this monolith. So let's go back to what I said about planning. You should start with the easy and low risk stuff, but then you should try to get going, get rolling. Deploy multiple pieces at once. We had dozens of endpoints to move in our API migration, so we were deploying 4 or 5 at once, 2 or 3 times a week at the peak. The goal here is balancing speed against risk, so move fast and don't break things. And finally, you can cheat. This is where I come clean. Say that you're going to get to a point in replacing your monolithic code where you're down to the long tail, the stuff that handles 10 requests a day, or just really isn't worth rewriting because the logic is so trivial and you don't want to have to move it over. Leave it where it is. We actually still run some of the PHP API code. The difference is that we moved it out onto its own role, and it lives behind Starship. Nothing says we can't proxy to something that already speaks our public API interface. And what you should really do here, this is a technique for you to cut off the long tail and not waste your time doing the stuff that isn't worth it. But you're also at the same time putting a wall around your old code, right? So leave it behind that shim, leave it kind of walled off, because it handles stuff that you need to get done, but you didn't want to have to add to it, right? So make it more attractive for everybody in your organization to follow the new rules rather than going back to the old way and chucking stuff into the monolith. That's all I've got. I think I actually have a couple minutes for questions. So brings me to the end. So to recap, big bang rebuilds are prone to failure. You should replace things incrementally. And we went through how Twilio used this technique to replace 500,000 lines of PHP with microservices, and how we employed best practices for architecture, testing, and deployment to move 5 billion monthly requests without downtime. So thanks. I hope I helped you learn something. And yeah, we've got 3 minutes?
Yeah, 3.
Great. Thank you.
So if you have questions, come up the front. I will start with one.
Thank you.
So you mentioned that the older PHP API, things would slow down, and of course, when you slow down, that decreases the user experience, and then all of that, and then there's sort of financial long tail sort of things from that. Yep. Do you think that such a large scale refactor is as far as economics go, a choice that companies should do without severe planning ahead? Like when people say we should rewrite this in this new hot language, at what point do you think that the cost is worth the reward?
Yeah, so to speak off the cuff, please don't quote me on this, but we had experienced several hour outages due to the PHP codebase's performance problems, right? So SMS database would fall over, and we would spend more time picking up broken PHP FPM workers and putting them back into the pool to serve requests than it took us to actually pivot the database master. So I think that's an obvious example on the side of, yes, please do the rewrite. And so yeah, I think that it's worth considering what is the economic cost in terms of developer overhead or outages if you have SLA violations and have to give money back to your customers. Against the amount of time it's going to take to actually accomplish this. And as I pointed out kind of at the end, you can always go part way, right? The advantage of doing the incremental refactor is that you can stop at whatever makes sense, right? So you don't have to do the entire thing if it makes sense to just extract the really high value pieces and then leave everything else where it is.
Thank you.
Hi, thank you, great talk. So time is always limited. So how did you manage the efforts of the team or the number of people working on this project between fixing bugs and adding features to the older code base and the newer code base? And how did you convince management of all of this?
So we actually, thankfully, the thing working in our favor here is that we'd proven the architecture by rolling out Starship kind of for some new features that nobody wanted to implement in the old code base. And when we kind of made the cut was when we said, okay, good, we're not going to add features to the new code, the old code base anymore. If you want new stuff in the API, you have to build a new internal service and use the new pattern. And so we had been in that mode for a long while. And then it was mostly a matter of convincing management, actually, as I kind of just answered the last question, that the cost of those outages was less than or more than the cost of migrating everything out of the old systems and actually getting replacements built internally. So yeah, unfortunately, I don't have a really good answer on how to convince management to let you do things like this, aside from arm yourself with the facts, measure the cost of whatever it is in terms of developer time or outage time, and point to it and say, look, if we invested 6 months here, we could stop doing this.
Thank you very much.
Thank you.